Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel, and on this auspicious and the most magnificent day of independence, I'm now going to discuss with you the rule 3 to convert non-exact first order ODE into exact form. Okay, so likewise, we have discussed in our previous two videos related to the same topic, if we come to know that we are having a differential equation of this type, which apparently looks like an exact form or total differential equation form, but once when we check, we come to know that the partial derivative of this thing with respect to y, it is not equal to the partial derivative of n with respect to x, which are actually m is your f of x, if we consider m as f of x like this, and this was our f sub y that we further differentiate with respect to x, is definitely not going to be equal, then it means that this equation is not total differential equation or exact differential equation. We have to convert it into exact form. Presently, this is non-exact. So if rule 1 and rule 2 methods of finding integrating factors, they are not helping us out, and still we are not able to convert this non-exact into exact form, then we move to rule 3 and we try to figure out whether the integrating factor so obtained through rule 3 is helping out this issue or not. Okay, so rule 1 and rule 2 methods are discussed in video 1 and 2 of this series. You can check it, the links are mentioned in the description box. So what is your rule 3? In rule 3, we just try to check that we just use this strategy that if our x into m, if we multiply this function with our x and we multiply this n function with our y, and if the summation of these two things, or these two terms, or these two functions, whatever you want to say, if they are not equal to 0, and in that case rule 3 is helping you out, and we are going to use integrating factor, or in other words you can call this integrating factor as mu of xy, is going to be this. Okay, this method is a little bit different like that of the last two ones, so that's how we do. Okay, so once when we obtain this integrating factor, we are going to multiply this integrating factor with this non-exact first order ODE. It looks something like this, and then we are going to use the same strategy that we use for the exact differential equations to find out the solution, which is actually a function that is going to satisfy it. Okay, so let us now try to see an example related to this condition. So here we go, this beautiful example. Let us close it in a box just to highlight this thing, so it's not going to mix with our solution work. Okay, so over here we are provided a beautiful differential equation which looks like exact form, but we have to check whether it is exact or not. So this is of the form like this. So if we just try to compare this general exact differential equation with this equation, with this question equation, come to know that m is this and n is this. Okay, so m is x squared y minus 2xy squared, and our n is, we are going to include definitely this negative sign, so I'm going to arrange my terms of this n function with respect to its signs. Okay, So this is going to be the positive term, this is going to be the negative term. So that's how we write. Okay, and then now let us try to differentiate this m with respect to y. So once when we differentiate this expression with respect to y, we are going to keep our x as constant. So we are having x squared here, and it's going to be 4xy. Yeah, that's it. And let us differentiate this n with respect to x. This time y is going to be kept constant. So we are having now 6xy minus 3x squared. Okay, so you can see that your partial derivative of m with respect to y is not equal to partial derivative of n with respect to x. So this equation, which looks like exact, is actually non-exact. So I'm not going to use the first two rules, because you can check it by yourself after examining the description box links. They're not going to help us out here. Okay, so we just directly approach to our rule 3, because rule 1 and rule 2 are not going to provide you integrating factor that is going to convert this equation into exact form. So now let us try to check the fate of your rule 3. Okay, so let us apply our rule 3 here. So we are going to multiply our m with our x and our n with our y. And let us try to find out, is it going to give us 0 or non-zero thing? Okay, so multiplying our m with our x, multiplying our n with our y. Okay, so we are just trying to solve this thing out. It's going to be x cubed y minus 2x squared y squared minus x cubed y plus 3x squared y squared. This and this gets cancelled, and this is giving me x squared y squared, and this is going to behave as your integrating factor. Okay, which is this. Okay, so not actually, this is your integrating factor. The reciprocal of x squared and x squared y squared is going to behave as your integrating factor. So integrating factor is going to be this. Okay, the reciprocal, I just forgot, it's the reciprocal. Okay, so now once the integrating factor is at our service, we are going to multiply this factor with this entire equation. Let's see how it looks like. So we gently multiply both sides of this differential equation with our integrating factor, we get this. So now you're going to divide this x squared y squared, this denominator thing, with both these terms and these two terms individually. Let's see what we get here now. So once when we divide this term with this, we are going to get 1 upon y here. Same process we are going to apply here as well. So it's going to give me 2 upon x minus x upon y squared minus 3 upon y. Yeah, that's it. Okay, so you can also arrange, if you don't like this negative sign here and you feel that you are getting a bit irritated with that, you can help this thing out as well by multiplying this sign with these two terms. So if you just change this thing plus, and you're putting the impact of this negative sign of the terms which are inside the brackets over here, Just going to make this thing positive and this thing negative, so you can write like this. That's how you arrange. Okay, like this. Okay, now you can see that this is your m and this is your n. Check the exactness now by differentiating this m with your y, this n with your x, one by one, and see, are they equal now? Definitely they're going to be equal, but we have to see it. So let's see, it's 1 upon y minus 2 upon x. That's what we are going to do. So once when you just differentiate this thing with respect to your y, you're going to keep this thing, the term involving x, as a constant. So the derivative of this term will give you 0. Okay, and the derivative of 1 upon y, or y power negative 1, is going to give you minus 1 upon y squared. Alright, that's it. In the same way, once when you differentiate this n thing, or n function, or yeah, also you can call it the partial derivative of the solution function with respect to y, you can also call that with respect. Now we are going to differentiate this n with respect to our x. This time the term involving y are going to be kept constant, so this thing derivative will be 0, and over here I'm going to get 1 upon y squared once again. So I'm going to get 1 upon y, negative 1 upon y squared. So now you can see that this thing is equal to this thing. This equation is 100% exact. This is your exact differential equation now. We have just transformed, we have just reduced this non-exact differential equation into an exact form by using your beautiful rule 3. Alright, now we are having exact equation. Now the next step is to find out the solution of this equation. Okay, so we are going to make some nice demarcation here. We're having enough space, so let me make a demarcation, then we proceed the work. Okay, now we are going to consider, now this thing has been proven exact. It means it's the total differential equation. It means this thing is the partial derivative of your solution function with respect to x, and this is the partial derivative of your solution function with respect to y. So you can also call this m as the partial derivative of your solution function with respect to x. This f is something that we have to find. This is our objective. Okay, so this is what you say, it's 1 upon y minus 2 by x. This is it. And in the same way, your n is the partial derivative of your solution function with respect to y, and this is your 3 by y minus x upon y squared. Okay, this is it. Now what we do, we are going to consider this m thing, or this partial derivative, which is your m. We are going to consider this thing, and we will integrate it with respect to x in order to free our function f. Okay, I'm going to integrate this m with respect to x. It's going to be like this. So now your f is free, and you can also write simply x, or also you can express it in the implicit form like this because this entire equation is a bivariate differential equation. That's why you can express your function in a bivariate form as well. It's your choice. So now as we are integrating the integrand with respect to x, so the terms involving y are going to be kept constant. So we just write the constant stuff outside the integral. It's going to behave something like this. Alright, so now you're having x upon y. This is a basic integration, no need further elaboration. This is the ln of x plus some constant. We are going to write constant here, h of y, because this is a constant. That's why the derivative of this constant was 0. That's why we're not having anything over here. Okay, So that's it. We just call this equation as our equation number 1. Just close it in a box nicely. Now you pick up this equation number 1 once again and differentiate it with respect to your y. Okay. So we just take the reference of our equation number 1. We are going to differentiate this function with respect to y. So when we differentiate this entire thing with respect to y, we are going to keep the terms involving x as constants. Okay. So x is kept outside, something like this. Okay. We have applied the operator on all these 3 terms. So now you see it is going to give me negative 1 upon y square. It's going to be written like this. This thing will become 0 because it's a constant term. The derivative of a constant thing is 0. So this whole thing will become 0, and this is going to be written like h prime of y. Okay, and this is your partial derivative of f with respect to y, and this was actually your n. Okay, this was actually your n. Now we can write the n value here, which was this. Okay, 3 by y minus x upon y square equals to minus x upon y square plus h prime of y. These two things will get cancelled. We come to know that h prime y is 3 upon y. Okay, now our objective is to find out the major thing that we have to find is h of y. So this is h prime y, the derivative of h of y. And now integrate this thing with respect to your y in order to get your h of y back. Okay, so integrate now. Just like that. So h of y is now restored, and the derivative of reciprocal of y with respect to y, integral of reciprocal of y with respect to y is your ln of y. Okay, plus some constant. It's up to you whether you want to write constant or not. That's it. And this h of y is now obtained. You're going to substitute this h of y value over here, and our function will be so evaluated fully, or so explored fully. This some constant. So this is going to be your function. Okay, so this was the function. Once when it will be substituted over here, it's definitely going to be satisfied. Okay, so that's all for today, and I hope the rule 3 method has been entirely cleared in your mind. The concept is cleared. So if you really feel this concept is cleared with the help of this video after watching it to the full length, I humbly request you to subscribe to my channel, honor my channel by your subscriptions and your likes, and don't forget to put your comments in the comment box below. And also I recommend you to watch the related videos whose links are mentioned in the description box so that you will get fully saturated related to this topic. Okay, take good care of yourself, and I'll see you in future with more helpful videos. And happy Independence Day to all Pakistanis. Allah Hafiz.